Okay, hello students, you welcome to chapter 3 part 7. This part is called Optical Troubleshooting. Okay, chapter 3 part 7 called Optical Troubleshooting. Okay, so let's quickly move on. Without much ado, let's begin. Now the first part is what we call optical troubleshooting, which is chapter 3 part 7. Now let's quickly look at the very first part. Troubleshooting itself, what is the meaning? What does it attain? Troubleshooting is like trying to find a way to resolve the problems that comes with optical networks and optical devices. There are several techniques that we use to measure and troubleshoot fiber links. You know, they have these links. There might be some problem due to mechanical micro-bending, due to so many factors causing problems in these fiber links. So finding these problems and finding solutions to them is referred to as troubleshooting. So a common technique that is used is called the optical power meter to determine power loss. So one of the big techniques that we use to troubleshoot, or method that we use to troubleshoot problems or faults in optical links, is called the optical power meter. We use the optical power meter to help us determine how much power is being lost in the system. So the tool we usually use, the techniques is optical power meter. Okay, then the tools we usually use, one of it is called virtual fault locator. A virtual fault locator, VFL. It's a device that is used to shine light down to the fiber to help locate any broken glass. You know, optical fiber is made up of glass. So the visual fault locator, what it does is to help us shine light into the glass. To shine light into the glass. Once that is done, once light is shown to the glass, then we'll be able to see any broken part of the fiber. We'll be able to see any broken part of the glass of the fiber. Is that okay? So the virtual fault locator is a tool. Is a tool that we use to troubleshoot fiber link, to troubleshoot fiber links. Okay, is a big tool we use, and the method is called, or the technique is called, optical power meter. Okay, now here is a fiber testing, OTD. One of the tools, or one of the measurement techniques, is called the OTD. OTD is the instrument. Okay, the instrument we use to measure. The way you use ohmmeter to measure resistance, ammeter to measure currents, voltmeter to measure voltage, or put simply, you use a multimeter to do all of these basic electrical measurements, right? The same way we use for optical, we use OTDR, which is optical time domain reflectometer. Okay, optical time domain reflectometer. This is the symbol. This is the symbol of optical time domain reflectometer. This thing, let's highlight it. Use a pen. Let's use a pen. This symbol, the whole of this symbol is called optical time domain reflectometer. This one. So once we measure it, whatever it will measure power in decibel, okay, per the kilometer or per the distance, power per distance in decibel, power in decibel per distance. So this one helps us to test whether the fiber is okay or has leakage or breakage and so on and so forth. So this is an instrument for measuring how much power is present in an optical fiber. Okay, so this device is called OTD, optical time domain reflectometer. And how it does it is just simply by reflecting light into the glass, and they're being able to calculate the power, how much power is present there, how much light is already there. So the OTD is a common instrument used for measuring optical fiber cables. So when you want to carry a measurement of optical fiber cables, we use the OTD arrow. Is that okay? Okay, now let's move on quickly. We erase, right? Okay, sorry. Let's. Okay. Okay, now let's move on to the next phase. Now the OTD, this one that we've just displayed, this OTD, this is the result. When you carry out measurement, this is what you see. Okay, the OTD arrow test, you can see we have the first point at A, then we have B here, we have C here, we have D here, we have F and G here, we have H here. You can see the signal wave. You can see the signal wave at every point. We're going to describe this measurement result, and then we also describe for figure A and figure B. We're going to this is the result from OTD arrow testing. Okay, like I said, OTD means optical time domain reflectometer. It's an instrument that is used for measuring the optical fibers. Instrument used for measuring optical fiber cables. So how much power is in it? In decibel. Power is measured in decibel in this regard. Okay, the power you calculate, you have to put in decibel. You've learned this in your A level, how to put values in decibel. So the power in decibel plotted against the distance that you get a graphical waveform. These results you can get it from using MATLAB. You can use MATLAB or Simulix to get these results. Okay, now here we say these are traces obtained from the optical time domain reflectometer, right? OTD arrow, for two different sets of multimode fiber. These are two different fibers, and both fibers are multimodes. That's why you see the wave variations are more than once. Okay, at F here, this is the end of the result, or this is the end of the measurement of the fiber. Here could be from the noise. What you see at G here could be from the noise. Here, what you see at I here could also be from the noise. So this one also the result of the fiber end at H. What you see here at I could be from the noise. You can see this distance is in kilometer, while this distance is in meter. This is a plot of decibel against distance in kilometer for figure A, and this is a plot of the power output from the OTD arrow against distance in meter. Is that okay? Now we're going to look at them one after the other. Okay, now this is called shooting the fiber. This in engineering, when you when you are in the industry, you hear the word shooting the fiber, right? The OTD arrow sends light pulse. How it works? How does this OTD arrow work? This one, this device will send light pulses, just like the same way this X-ray send light into your bones to take some measurements. So this OTD arrow send light pulses into the fiber. Okay, it send light pulses down to the fiber and measures the reflected light. So what it does is that it sends light to it. This OTD arrow is capable of sending light into the fiber cable, and then when light is shone into the fiber cable, how much of it is reflected is the value we get in power. Okay, we calculate the power of that value of the reflected light. So the power of the reflected light plotted according to the distance, how far it's going, then gives us a range of values like this, gives us a plot like this, an engineering plot like this. Okay, so this is how we measure the power in the cables, in optical fiber cable. We use OTD arrow to test how much power is in the cable. If the cable is faulty, if the cable is broken, we got to find out. If the cable, the splicing of the cable is mechanical, like as you see in this one, we got to find out. Okay, we got to see that. Now let's move on to the next one. Now the OTD arrow enable the installer or the maintainer, the installer administrator, network administrator, or network technician, whoever the installer is or status you are, or the maintenance crew, to verify the quality of each fiber, the lifespan of each fiber, and also obtain some measurement performance, how the fiber is doing. So you can, with this OTD arrow, you can tell about the quality of the fiber, the lifespan of the fiber, how long you think it can. The OTD arrow meter is able to tell you the lifespan of this fiber, or you're able to see it from your calculated result. how long this fiber can stay. And also get some measure of performance, how well it's doing, like you, as you see now, how well it's doing, how the decibel value is degrading, is going down, or as the signal is losing power with time or with distance covered, how the signal is losing. You can see it's going down from here to here to here. The value is going down, till it even gets at H, it gets so low to this certain value if you trace it to the vertical side. So how much power is being lost as you transmit over this cable over time, based on how many distance is covered, you will be able to see the system performance from using this OTD error testing device. Okay, now if you look at this graph, the x-axis on the trace indicate the distance. I already explained this. This is the x-axis according to physics, or your graph in mathematics, basic mathematics, arithmetic, or basic mathematics in secondary school. So you see this is your horizontal axis, which is your distance axis, or right, and then the vertical axis is your power axis, whereas the y-axis indicate the measured optical power value in decibel. I already explained this. Let's move on quickly. Now let's take a look at, let's describe or discuss only the first graph. Okay, let's describe or discuss only this first graph. Excuse me. Now still on test E. Now we say in regard to the test on this figure A, now we look at point A is a dead zone. This point A is a dead zone. We don't read these values, we don't use this value. It's a dead zone, we call it a dead zone, or a point too close to the OTD arrow. It's too close, so you cannot ensure optimization of value obtained here. The values here will not give you a reflection of what is actually the real value. So it's too close to the OTD arrow device. The value you get here are said to be too close. They are too close to this device. Okay, just the values from here they are too close to the device, so we cannot give it a judgment. So we move further away from the OTD arrow on the cable. The closest part of the cable to the OTD arrow value that we got is not what we're going to use for absolute judgment. So we move further a little bit away and take value at point B. Okay, so we say the dead zone, or the point too close to OTD arrow for measurement to be made. So this one we cannot rely on that value. Now let's look at another point and see which value we can get. The measured value begins at about 25 decibel. Now if you look at here is 20, 25 will be somewhere here. You see this point? The measured value begins at about, okay, let's say, okay, from here, because from here we start taking the, you know, A is the beginning of this part this way. A, where the graph start to slope upward here is A. Where it start to go upward, the wave start to go upward, that's A. Now where the end of it, when it comes down, slope down, the end of it here is the beginning of B. Is the beginning of B, and that value is somewhere around 25 decibel, and it decreases in value as the distance travel increases. So this value, you can see this is sloping down gradually. This value is going down as the distance travel increases, coming down to almost 20. But at the end of B here, this way, the value is already 20. Okay, 20 decibel. It decreases so as your distance increases. This is your distance axis. As your distance increases, you lose power. The power of the optical fiber, or the optical fiber power in decibel, is decreasing as the distance increases, right? So at this point we say a disturbance in the light propagated down the fiber occur at point B. So there's kind of a wave disturbance at point B, so we can start taking measurement from B. Now let's move on to the next one. This is an example of what a poor quality splice looks like. What you see here is a poor quality splice in regard to the reflection as well as insertion loss. The reflection coming out and the insertion loss. Remember, insertion is attenuation. You can see the value is losing very fast. The value is losing very fast. You see, it's losing its value, its content very fast, its signal very fast. So most likely this is a mechanical splice. So mechanical splice, remember we said there's air gap. So if there is no this gel to change the surface area of glass to glass to air to glass to glass to glass to glass, you know that glass to air glass air glass interface has to be improved upon to look like glass interface. So if there is no such interface, then the result looks like this. It's not going to give a very, because there will be great loss. There's huge loss in the value of the signal. Now this type of event occurs at point C and D. At C, you can see the value has really gone down. If you see the end of C and the end of D, and by D you already got it 20 decibel. You already get it 20 decibel. About 5 decibel is lost already. About 5 decibel is lost from 25 to 20. So for this distance covered, about 5 decibel is already lost. About 1.5 kilometer. This is 1.5 kilometer. Here is about 1.6 or 1.7 kilometer. At D, you've already lost about 5 decibel. That's a huge number. It shows that there's poor splicing taking place, and this could be coming from a mechanical splice of the cabling. Okay, these are also most likely mechanical. You see, that's what we are saying, that this is mostly likely mechanical splice. Now let's take a look at points F and G are mostly likely the jumpers problem. This because they are super close. These are jumpers error. If you look at this point F, we say C and D coming from the system. F is the jumpers error. Remember, we describe a campus network, we talk about the jumpers like the cabling. Okay, this is the jumper at the patch panel connection of the fiber end. So the drop in value is coming as a result of the jumper and the patch panel. Okay, then the steep drop at point H, look at H all the way down to this place. See, H is dropped from here. G, you know, the bottom of G is here. Now at H is dropped all the way to this value. This value is around 10 decibel. You can see at the bottom of H this is about 10 decibel power. So there's a huge drop from around 20 to 10. So this is too huge. Now we say the steep drop at H is actually the end of the fiber. So at the end of the fiber, your 25 decibel power dropped to 10 decibel power. So that's a huge drop. Now the point I, what you see here is typical noise that came into the cabling. Noise that occur at the end of the terminated fiber. So the fiber that you did not terminate, noise get into it, and those noise amount to this signal that is being added to your signal. You can see it's quite different from the power that you are transmitting. So this noise is coming from the end of the cabling that is not terminated. Now let's take a look. Notice at point G, that's what we notice at point G, that the overall value of the trace has dropped to about 17. Now let's look at G, the end of G, the bottom end of G. If you trace the bottom end of G, is no more 20. The value has dropped to 17. The value has dropped to 17. If you trace this bottom end of G, the value has dropped to 17. Okay, so we say if you look at G very well, the value has dropped to 17 decibel. There has been about 8 decibel of optical power lost at the end of the cable. Why 8? Because we started with 25. Remember, we started with 25. So 25 dropped down to 70. So we've lost 8 decibel altogether. And before we had this issue with H. And remember, we say I is just noises that came into the terminated cable at the end of terminated cable. The cable itself ends at this point G. Okay, so there has been about 8 decibels of power loss in the cable in the 1.7 kilometer run, and the distance is about 1.7. See, if you trace this one here, about 1.7 kilometer run, you've lost 8 decibel. So that's not good enough. Now let's look at B. You know, the first one is the figure A. Let's look at figure B. On figure B, the hump at point A, this one, This hump at point A is basically also a dead zone. Remember, we say we don't read the values, we don't start using the values from point A. We start reading them from B. We start reading them from point B, and point B starts sloping down from here. Okay, the point where it starts sloping down is B. Okay, so we don't read this one. A is a dead zone, and the OTDRO cannot typically excuse me, OTDRO cannot typically return accurate measurement value in this region. So every region you measure at A, the part that is where the cable is too close to the OTDRO, are not usually correct or accurate measurements. Okay, that's why we don't start counting from this region. So we start looking at the value from B. We start looking at the value from B, the end of B. What value do we have at the end of B? The useful value information begins at the point B with a measured value of 20 decibel. Look at it, the end of B. You know, B starts sloping down from here and ends somewhere here on this horizontal flat line. So you trace it here is 20 decibel. The power is 20 decibel. So that's the end of B. That's where we start taking the values, okay, of the signal, of the cable, of the value of the signal in the cable. Okay, A is a dead zone. We call it a dead zone. We don't start taking the values from there. Then point C, you can take a look at point C. Point C starts from here all the way to this place. Okay, then we say point C shows different type of event. Now what could that event be? This type of event is typical of coiled fiber, coiled one, the coiled fiber. This point C value, you can see it's so wide. It covers a long range of distance and is having almost absolute close power constant. Okay, so we say this is a typical coiled cable or fiber that has been tightly bent. A fiber that has been tight, that's why the range of value over a long distance is almost closely constant. Okay, you can see we can say the fiber is tightly bound together, closely bounded together. Now, or you can say possibly with a tie wrap, a very big wrap, a tie wrap, or that has had some other disturbance affecting the integrity of the fiber, because normally the waves are not this displayed constantly over a long period of or over a long period distance. Okay, the waves are not like this on a straight loop over a long distance. So for you to have this type of result, it means at this point the fiber was tightly wrapped. Okay, so that's for point C. Point D and F, look at D starts from here and goes all the way to this place, and then F start from here and all the way to the end of this place. So this is obviously the end of the fiber cable. This is obviously the end. What you see at G is the noise or terminated part of the noise that comes in, okay, at the terminated of the fiber. So we say point D and F are usually the end of the fiber. This one, D and F, is the end of the fiber. Okay, this is the end of the fiber. At point D, the trace level is about 19. Let's see. The trace level is about 19. If you trace this one, that is a little bit less than 20. So it's just 1 decibel lost, right? At point D, the trace level is what? The trace level is about 19, which is just a loss of 1 decibel, right? Yeah, see, 1 decibel lost. There's only 1 decibel lost, right? The loss is about just a decibel this way, this place. About 1 decibel lost. That's what you lost. So at point D. So you imagine you had 20 at B. You know, we start measurement at B. 20 at B, which is the power that's being transmitted, 20 decibel power signal be transmitted. But at point D, you only had, up to point D, you only had 1 decibel lost, right? You only had 1 decibel lost. Okay. What I'm using now is a laser pointer. See, this is a laser pointer, a laser light. Okay, that's what we use in optical signal. We transmit this one, this light you're seeing that I'm shaking. This is a laser light. This is what we use in optical fiber communication. You know, laser diode. or diode laser is the most diode laser is the most source of the light used in optical fiber communication, right? That's what I'm using now to explain this graph. Now we say point G, this G is just the noise that occurs at the end of the terminated cable. Okay, this is just the noise. Now why is this why is this the noise coming from a terminated cable, whereas the other one, the one we looked at before, is the noise from alternated cable? You can see there's a continuity here. This noise is coming from alternated cable for figure A. Now for figure B, the noise is coming from where? Terminated cable. It's coming from terminated cable, this one, because it's not a continuity. It got to 0 before we had this noise. This noise is coming from a terminated cable. Let me highlight it, use a highlighter. So we have to take note of that. This one is coming from a terminated cable, this one. The noise at point G. At point G is coming from terminated cable, because you can see there's no continuity between F and G. It goes to 0 value, 0 decibel before we had this noise signal. So this is coming from a terminated cable, or like the first diagram. The first diagram, the value is coming from all terminated cable. This one is coming from terminated cable. Figure B is coming from terminated fiber cable. Okay, let's begin by continuing with our laser pointer. Let's continue with our laser pointer. Now let's go to the next part. The next part is the end of the things that we have used. So this is just about what you need to know, how to measure the power using OTD error, and these are the measurement, how we read the values, where the values add the noises that gets it to it for both terminated cable and alternated cable. And then this is all about the troubleshooting, and these are the terminologies we've used. We say we use the visual fault locator to shine light. A good example of a visual point locator is a visual point locator is used to locate fault on the cable, whereas OTD arrow is used to carry out the measurement. OTD to measure the value, the power over the distance the cable was the signal was sent through. Then we talked about inverse. So these are the terminologies that we use in this case. Thank you, and this is the end of this chapter, the entire chapter 3. This is the end of the entire chapter 3, and this is Waidsum University, the fastest growing digital and online and virtual university in the world. So we implore you to continuously come to us and learn with us. Okay, we are the new face of education. We are the new era of education. Okay, and we say thank you for joining us. Thank you for joining us. This is the end of our today's class. Thank you.